Viewers, welcome to our lecture video. In this lecture video, we are going to do the analysis of this frame. Analysis of our frame means we are going to find our axial forces, shear force, and bending moment diagram of this frame. And I'll be explaining each and every portions clearly. So do watch the video till the end to understand the concept clearly. So right now in our frame, what you can see here is we have our portion AB, portion BC, and portion CD. We have hinge support at the point A, and we have our roller support at the point D, and we have a uniformly distributed load of 10 kilonewton, 10 kilonewton per meter, which is acting at some angle at our member CD. We have a clockwise moment of 10 kilonewton meter for our member BC, and we have a force of 10 kilonewton acting at the point B, which is at a midpoint of AB, which is 2 meter from A or 2 meter from B. And now we'll be doing the analysis of this frame. So first and foremost, before doing our analysis of frame, what we need to do is we need to know whether our frame is a determinate or indeterminate. So right now, in order to find out whether our force is determinate or indeterminate, firstly we are going to write down the reaction forces of our frame. So what we have over here is, since this is a hinge support, we are going to have two reactions. First reaction is going to be acting vertically, RAY, and second is going to be acting in horizontal direction, it's going to be our RAX. And for our roller support, we are going to have only one support reaction in our vertical direction, is going to be our RDY. So in order to be statically determinate, what we know is, so right now we are going to solve our frame which is statically determinate. And now let me write down over here we have our available support reactions. Available support reaction equals to 1, 2, 3. So right now we have our available support reaction is 3, which is our unknown. We can write out this as our unknown, or our available support reaction is denoted by R. And we have our equation of equilibrium. We are going to have three equation of equilibrium, which is going to be our EFX equals to 0, EFY equals to 0, and EM equals to 0. So right now we have now R minus 3, which is, now we have three unknown support reactions, which is 3. We have three equation of equilibrium, this 3 is of this 3, which is equal to 0. So right now our this frame is statically determinate. So you can show this as well while doing your frame analysis. So right now our frame is statically determinate. So in our next step, now our actual step will begin. So right now we have our step 1. So what is going to be our step 1? Our step 1 is going to be our calculation of support reaction. So before finding out our axial forces, shear forces, and bending moment, first and foremost we need to calculate our three support reactions, which are RAX, RAY, and RDY. So first and foremost we will be calculating our support reactions. So step 1 is our calculation of support reactions. So before calculating our support reactions, let me tell you one important point. While calculating our shear force and bending moment, which we'll be doing at a later portion of our video, we'll be following a certain set of sign conventions while moving from left to right or while moving from right to left. For both of our shear force and bending moment, we are going to follow certain rules and certain sign conventions. But while calculating our support reactions, we don't need to follow any sort of sign conventions. We can take our clockwise movement as positive, we can take our upward forces as positive, and we can take our forces acting at right as positive, or we can take vice versa as well. We can take our forces we can take our anti-clockwise movement as positive, we can take our forces acting in downward direction as positive, or we can take our forces acting at left as positive. We don't need to follow any sort of sign conventions. But this is while calculating our moment only. While calculating our moment or support reactions only, we can follow any sign conventions, but we need to follow a uniform one. But while calculating our shear force and bending moment, we need to follow the conventional sign convention only. We cannot use the other one. So firstly, while calculating our support reaction, what I need to do is, we have three equation of equilibrium as I mentioned before. EFX equals to 0, EFY equals to 0, and EMY equals to 0. So we are going to use this sort of equation. But before using our equation of equilibrium, firstly I am going to convert this 10 kilonewton per meter into point load. So firstly, this is going to be my first step. So let me draw one perpendicular line from here, and let me draw this line as well in this direction. So what I need to do is, firstly I need to find my inclination. I need to find how much my member CD is inclined. So I need to find this theta, and as you can see here, this length, this horizontal distance is 3 meter, while this vertical distance is going to be 4 meter. So this much is equal to AB. So 2 plus 2 is going to be 4 meter only. So I need to find my theta. So let me write down over here my tan theta. So I'm writing it over here. So my tan theta is simply going to be 4 upon 3. So my theta is going to be equal to 53.13 degree. Now I need to find my length CD as well. So I'm going to simply use my hypotenuse rule, which means my length CD will be simply equal to root over 4 square plus 3 square, which is equal to be 5 meter. So my length CD is also equal to 5 meter. So next what I'm going to do is I'm going to convert this UDL, uniformly distributed load, into a point load. So in order to convert my UDL into point load, so let me put it this way. I'm going to convert it into my point load. So right now my value of UDL is 10 kN per meter, and it is acting at a span of 5 meter, and it is acting at a span of 5 meters. So in order to convert it into point load, I simply need to multiply 10 kN per meter with 5 meter, which is going to be equal to 50 kilonewton. 50 kilonewton, and right now this 50 kilonewton is acting at a distance of 2.5 from point C and 2.5 from point D, because our point load is going to act at midpoint, is going to act at midpoint of our total span. So 2.5 meter from C and 2.5 meter from D. So now next we are going to find our in order to find our support reaction, what we are going to do next is we are going to take moment about A, and we are going to take clockwise moment at 0. So you can take anti-clockwise moment at 0 as well. There's not going to be any difference. So right now I'm going to take EMA equals to 0. You can calculate your moment about D as well, but right now I'm going to calculate moment about point A. So while calculating our moment, it is very important to understand that moment is simply equal to force into distance r, but this distance r is our perpendicular distance. This is a very important point. We have moment equals to force into distance, but this distance r is our perpendicular distance, no any ordinary inclined distance. This is going to be our perpendicular distance. So as you can see here, this 50 kilonewton is acting at certain inclinations. So if we have to find moment about point A, we need to resolve this 50 kilonewton into its sine and cosine components. So firstly what we're going to do is now we are going to resolve this 50 kilonewton into its sine and cosine components. So let me draw it over here in order to make this a little bit clearer. I have my theta over here. This is going to be my 50 kilonewton force. 50 kilonewton force. Now I need to convert it into my sine and cosine component. So how will I convert into sine and cosine component? So I'm going to draw this line a little bit downward. So as you can see here, this is going to be theta, alternate angles. So directly you can do this. This is going to be theta. If this is going to be theta, this is going to be 90 minus theta, as this 50 kilonewton will be acting perpendicular to member CD. So our member CD, this is going to be 90 minus theta. This is going to be 90 minus theta, and if this is 90 minus theta, this is going to be theta. So our theta is going to be alternately theta, 90 minus theta, theta. So as you can see here, this angle is going to be our theta. So if I resolve this, the nearer side to the theta, a simple trick to find cosine and sine component is for our required resultant, the side which is nearer is going to be our cosine component, 50 cos theta, and the farther component is going to be our sine component, 50 sine theta. So 50 cos theta will be 50 into cos, we have our theta is 53.13. So 50 into cos 53.13 is going to be 30 kilonewton, while this is going to be our 40 kilonewton. So let me write this down over here, 30 kilonewton and 40 kilonewton. So after resolving my forces, finding my perpendicular distance, now I can finally calculate my moment about A. So in order to calculate moment about A, what I'll be doing is, firstly I need to see my forces. So right now I'm beginning from D and I'll go till A. So follow a certain pattern so that you do not miss all the forces acting while calculating our moment. So firstly, I'm going to move from point D. So I have point A over here and I have point D over here, and RDI is acting vertically upward. Since it is acting vertically upward, it is going to produce anti-clockwise moment. So minus RDY into 7. Because my perpendicular distance is 4 plus 3, 7, and RDY. So how RDI is producing anti-clockwise moment? So as you can see here, here is my member A, here is my member D. So let's just draw an imaginary line in order to make the concept clear. And D is acting vertically down, is acting in this way, RDY, and this distance is 3 plus 2, which is 7. So as you can see here, this is my point D, and if it's acting vertically upward, it is going to produce anti-clockwise moment, because right now my point A is fixed. As you can see over here, right now my point A is fixed, and if I push RDY upward, RDY is producing anti-clockwise. This is moving in this direction, so it is producing our anti-clockwise moment. So simply RDY into 7. since I am taking clockwise moment as positive, so anti-clockwise moment is going to be negative minus rdy into 7. So next I have now I need to see how my this UDL is producing moment about it. As I clearly explained before, moment is force into perpendicular distance. So 50. So we are not going to use 50 kilonewton, but we are going to use the cosine and sine component of 50 kilonewton. So right now 40 kilonewton is acting over here. So as you can see here, this distance is going to be equal to 40 kilonewton. So the perpendicular distance from point A is 2 meters. As you can simply see over here, since it acts at a midpoint and F is our midpoint, and the corresponding part over here is going to be our 40 kilonewton. Hope you have understood how 40 kilonewton will act at 2 meter, because our point load will act at the middle, and the perpendicular distance of this middle is going to be 2 meters. 2 meters, or you can simply do it in this way as well. This is going to be 3 meter. This is 4 meter. This overall was 4 meters, so this half is going to be 2 meter. So simply this is going to be my 2 meter, and 40 kilonewton. If we just push this, if we just shift this 40 kilonewton over here at point F. So in order to understand it better, we are going to shift 40 kilonewton over F. So 40 kilonewton is acting in this direction. So as you can see, 40 kilonewton is acting in this direction, which means it's also going to produce anti-clockwise moment. Same as of RDY, it also going to produce anti-clockwise moment. Plus minus 40 into perpendicular distance is 2. Hope you have understood how 40 kilonewton has produced anti-clockwise moment. It is as same as that of RDY. So let me just simply draw. Let's make the concept even more clear. So as you can see here, 40 kilonewton is acting in this direction. You can simply shift the force of 40 kilonewton from this portion to point F to in order to understand how the moment is produced. Here is our point A, and as you can see here, so if I turn my figure in this side, 40 kilonewton is also acting from downward, so it's also going to produce anti-clockwise moment as well. Anti-clockwise moment. So now this is going to be, and my perpendicular distance is 2 meters. So it's simply going to be minus 40 into 2. Next is 30 kilonewton. So we are moving from D to A. We have 30 kilonewton, and 30 kilonewton is acting vertically downward. So RDY was acting vertically upward, so it produces anti-clockwise moment. So right now 30 kilonewton is acting vertically downward. So if we shift the force down over here, it's going to produce clockwise moment. So next what we are going to do is plus 30 clockwise moment into what is our remaining distance. So our remaining perpendicular distance is going to be from A to this point. We have 4 meter. Since this is acting at our midpoint, since we are acting exactly at the half, so half of 3 is 1.5 meters. So 3 into, let me just put this as 4 plus 1.5 plus 30 into 4 plus 1.5 plus, now we are going to move. Hope you have understood why we have taken half, because this point load acts at the middle. So middle means half of 3.3 meter, which is 1.5. 4 plus 1.5 is going to be our perpendicular distance. Now we move towards our member BC. In our member BC, we have 10 kilonewton per meter, which is acting in clockwise direction. So this is simply going to produce clockwise moment, plus 10. Simply write this as plus 10. Now finally we have we move to our point F, and in our point F we have 10 kilonewton. So let me show it in this way. 10 kilonewton is acting vertically downward, so again anti-clockwise moment, same concept, it is moving downward. So as we move to our point F, 10 kilonewton is acting downward. So as you can see, if it is acting downward, it's going to produce clockwise moment in this way, clockwise moment. So we are going to write this as plus 10 into perpendicular distance is 2 meter from point A, plus 10 into 2 equals to 0. So you need to follow a certain pattern, certain direction, so that you don't miss any forces. So on solving this, we are going to get our value of RDY as 16.43 kilonewton. 16.43 kilonewton. So after finding out RDI, what we are going to do is we are going to use our other equation of equilibrium, which are EFX equals to 0 and EFY equals to 0. So right now I am going to take upward forces as positive, plus EFX equals to 0. You can take downward forces as negative, as downward forces as positive as well. There is going to be no any errors. So let's see what are the upward forces. So right now I have a force of RAY acting upward. So RAY, I have RDY acting upward, RDY, while our 30 kilonewton is acting downward. Minus 30 kilonewton equals to 0. We don't have any other forces. So this is EFY. This is EFY. So right now we are taking force acting in y direction. EFY equals to 0, not EFX. We'll do that next. Right now we took forces acting in y direction as 0, and forces acting upward are taken as positive. So we have RAY, RDY, while 30 kilonewton is acting downward. So minus 30 equals to 0. Next we just put the value of RAI plus RDY is 16.43 minus 30 equals to 0. On solving this, we are going to get the value of RAY as 13.57 kilonewton. 13.57 kilonewton. So finally, we are going to take forces for EFX, and right now I'm taking forces acting as right as positive. EFX equals to 0. So right now I have RAX plus 10 while minus 40 equals to 0. So as you can see here, we have only three forces acting in x direction. RAX, 10 kilonewton, both of them are acting at right, so we take at positive, and we have 40 kilonewton acting at left, we take that as negative. On solving this, I get my value of RAX as 30 kilonewton. Hope you have understood our step 1. So in this way we end our step 1. So in our step 1, what we did was we calculate our support reaction RAX, RAY and RDY using our three equation of equilibrium: EFX equals to 0, EFY equals to 0 and MA equals to 0. Hope you have understood till over here. Now we'll be moving towards our step 2. So before jumping into our step 2, what we are going to do is we are going to draw our figure one more time, but this time so let me tell you how we are going to draw our figure. So this time we are going to draw again we are going to draw our figure one more time, but this time we are going to show all the loads. We are going to draw it different. This is going to be my member AB, this is going to be my member BC, it's going to be my member CD. This is very important portion. So right now as we calculated before, so we are going to so let me show all my forces acting. So right now I have my RAX and RAY, so I am going to put those values. So right now before I calculate my values of RAY, so it's going to be RAY, this is equal to, so I calculated this value to be equal to 13.57 kilonewton. So I'm going to write that down. RAY equals to 13.57 kilonewton, and RAX as well. I found my RAX to be equal to be 30 kilonewton. So I have my one more force I'll calculate, which is RDY, three support reactions RDY, and I found my value of RDY to be equal to 16.43 kilonewton. Next I'll write down all my remaining forces as well. So according to my question, I had 10 kilonewton acting over here, 10 kilonewton and 10 kilonewton meter moment, and this 50 kilonewton as well. I'm going to write down all these forces. So I have my 50 kilonewton in over here acting at the midpoint, 50 kilonewton, and in my member BC I have my moment of 10 kilonewton per meter, and for my member AB as well at my point F I have, for my point F I have 10 kilonewton. So right now, after writing down all these forces, what I need to do next is I need to put my all these members in equilibrium. So before so what I did not tell at the beginning of the video is this: our overall frame is in equilibrium. Our overall frame is in equilibrium. Since our overall frame is in equilibrium, our individual members are also going to be in our equilibrium. So our member AB, member BC and member CD, all these three members are also going to be in equilibrium since our overall frame is in equilibrium. So in order to be in our equilibrium, so as you can see here, in our portion AB, a force of 13.5 kilonewton is acting upward. So in order to maintain equilibrium, what needs to happen is a force of 13.5 kilonewton must act downward. 13.5 kilonewton must act downward. If no such forces acting, the forces acting upward will push this member upward, and our overall frame or our member AB will not be in equilibrium. So in order to maintain equilibrium, a force of 13.5 kilonewton must act in opposite direction. Similarly, we can see here a force of 30 kilonewton and 40 kilonewton is acting in this direction. So in order to maintain equilibrium, a force of 40 kilonewton must act in this direction. A force of 40 kilonewton must act in this direction. So as you can see, we have been using our simple logic. Similarly, for our member BC as well, as you can see here, a force of 13.5 kilonewton is acting downward. So for our member BC, a force of 13.5 kilonewton must act upward. As you can see here, a force of 13.5 kilonewton must act upward, and for our point C, a force of 13.5 kilonewton must act downward in order to maintain our equilibrium. 13.5 kilonewton must act downward, and as you can see, a force of 40 kilonewton is acting in this direction. So for our member BC, a force of 40 kilonewton must act in this direction. Using the same logic, a force of since a force of 40 kN is acting in the right, in order to maintain equilibrium, a force of 40 kN must act at the left. A force of 40 kN must act at the left, and as you can see here, now we have done for our member BC, we have done our for member AB. So if you might be wondering why we have a 13.5 kN force acting upward. So let me draw my frame over here. Actually, this was my initial frame. So this is what my frame look like. So I have my A, B, C and D over here. So let me explain for one force, so you can use the similar concept for all the force. In our member A, I have 13.5 kN acting upward. So in order to maintain equilibrium, what happens is a force of 13.57 will act downward. 13.5 will act downward, and in order to maintain equilibrium, in order to cancel out this force, another force of 13.5 kN must act upward. So in our member AB, there will be two forces of 13.5 kN. For our member AB, it will be acting downward, while for a member AB, it will be acting upward. So in our point C, there will be another force of 13.5 kN acting downward. So this 13.5 kN will be acting all over our beam in different directions in order to maintain equilibrium. Hence, we can use our equation of equilibrium: EFY equals to 0, EFX equals to 0. So to basically simply understand the topic, if 13.5 kN is acting upward, in our member AB, 13.5 kN must act downward, while for our other point B, of our point BC, this 13.5 kN will act upward. This is acting downward, so it will act upward, and this is downward in order to maintain equilibrium for this 13.5 kN. Similarly, for our 40 kN as well, this is acting downward, so in order to maintain equilibrium, this must act upward. So act upward for our member AB, while for our member BC, this 40 kN will act in downward direction. And in order to maintain this, in order to maintain equilibrium for member BC, this 40 kN will act inward or in left direction. So for our member CD as well, we need to for our CD as well, we cannot write down forces as over here because we haven't calculated our shear forces already. So right now, with our calculated forces, this is what our figure looks like for our member AB, BC and CD. We'll be updating this figure once we calculate more shear forces and bending moment. So now moving to our second step. In our second movement, we are going to calculate our shear force and bending moment and axial forces, but we will be calculating all of those forces for our particular member. Firstly, we will be calculating our axial force, shear force and bending moment for our member AB, BC and then CD. Firstly, we will be calculating for our member AB. So now firstly, we will be looking forward for our member AB. So for our member AB, so let me write down for my member AB. So as I already explained before, our overall frame is in equilibrium. So firstly, what we are going to do is we are going to consider equilibrium of member AB. Consider equilibrium of member AB. So let me draw my figure for my member AB as well, my raw figure. So what does my figure AB looks like? This is my A, this is my B, and as I explained before, there is for my member AB, there is a force of 13.5 kN acting upward. So in order to maintain equilibrium, a force of 13.5 kN must act downward, and there is a force of 30 and then 10, which is 40, which is, so let me write down in this way: 10 kN and 30 kilo. Sorry, it's 30 kN and this is 10 kN. And next I have in order to maintain equilibrium, a force of 40 kN must act at joint B. So next what I'll be doing is first and foremost, we're going to calculate our axial forces. So in order to calculate our axial forces, we have axial force, let me denote it as NAB for a member AB. So what is axial force? Axial force are those forces which acts along our axis AB. So as you can see here, along our axis AB, or in that direction, or let's say in the parallel or along our AB, there is a force of 13.5 kN acting. But as you can see here, this 13.5 kN is acting inward. So as you can see here, if this is our member AB, so as you can see here, if this is our member AB, 13.5 kN is acting in this direction. Both of the 13.5 kN are acting inward, so it is actually compressing or squeezing our member AB. So for our, this is going to be our compressive force because they are acting inward. So for our inward force, we are going to take this as negative, minus 13.5 kN. Why negative? This is because this is compression. So we have calculated our axial force. Next we are going to calculate our shear force. shear force. So in order to calculate our shear force, what we can do is we can take a certain section x1 at a certain distance x, or we can simply calculate our axial forces as well. So let me calculate our axial force directly without taking any section. So right now I'm going to calculate our axial force at left of A. So as you can see here, at left of A, there are no any forces acting. So in order to understand our axial forces better, we can turn your figure in this way. So in order to define axial force, axial force are those forces which act perpendicular to our member. So as you can see here, perpendicular to our member, there's a force of 30 kilonewton, 10 kilonewton, and 40 kilonewton acting. So in that way we are going to calculate our axial force. So the most important thing which you need to remember while calculating our shear force are those forces which act perpendicular to our member, which act perpendicular to our member. So as you can see now, at left of A, there are no any force acting, so shear force is going to be 0 kilonewton. So now, as I talked before about sign convention, where we have to use certain sign convention while following our while calculating our shear force and bending moment. So in order to write down my shear force, as we are moving from left to right portion of our any beam, we are going to take our forces. While moving from left to right, we are going to take our upward forces as positive, while our downward forces as negative. So we need to understand this. We need to understand this about shear force and bending moment. And while we are moving from left to right, this is for my shear force. While moving from left to right, upward force are positive, downward force are negative. While it is vice versa for right to left, upward force will be negative while downward force will be positive. And similarly, while moving from left to right for our moment, bending moment, what we are going to do is we are going to take our clockwise moment as positive, while our anti-clockwise moment as negative. This is for our while moving from left to right for our bending moment. So now, using this sign convention, we are going to find our shear forces. So let me write this my point F. So right now we found our shear force at left of A, which is 0, since there are no any forces acting left of A. Now we're going to find our shear force acting at right of A, which is going to be VAR, and my shear force acting at right. So as you can see here, we are moving from A to B. We are moving from left to right portion of our frame. So let me show my frame over here. This is my frame, and we are moving from left to right direction, left to right. And as you can see here, while moving from left to right, we follow this sort of sign convention. And as you can see here, at right of A, we have 30 kilonewton, but this 30 kilonewton is acting downward. So while moving from left to right, downward force are taking as negative. So this 30 kilonewton is going to be negative, minus 30 kilonewton. So now we are going to take our shear force at left of F, BFL. As you can see here, at left of F also there are no other force acting, so it's going to be as minus 30 kilonewton only, since there are no other forces between A and F. Now at right of A, at right of F, we are going to have minus 30 kilonewton, minus 10 kilonewton, which is going to be minus 40 kilonewton. As you can see here, because 30 kilonewton is also acting downward. 30 kilonewton is also acting downward, and this 10 kilonewton is also acting downward. Minus 30 minus is going to be minus 40 kilonewton. And now as we move at left of B, now we move directly at left of B. This is going to be minus 40 kilonewton only, because there are no any sort of additional forces between F and B. And finally at right of B, BFR, we are going to have minus 40 kilonewton plus 40 kilonewton, which is going to be 0. So as you can see here, we need to have 0 at our end, and we have got our 0 at end. We have taken 40 kilonewton as positive, because right now we are moving from left to right, and upward force are taken as positive, downward force are negative. So minus 30 minus 10 minus 40, as you can understand till F. But as we move to B, minus 40 plus 40, 0. So minus 40 plus 40 kilonewton is 0. So we have our shear force at B equals to 0. So we'll be drawing our shear force and our axial force and our bending moment diagram at the end together. So next we'll be calculating our bending moment. So in order to calculate our bending moment, we can take our section x1, but right now I'm going to calculate directly. So first I'm going to take a bending moment at A. Bending moment at A is going to be 0 kilonewton meter, because our bending moment simply means force into perpendicular distance. So as you can see here, if right now the perpendicular distance from A is 0, so our R is 0. So as I already explained before, bending moment M equals to force into distance R, perpendicular distance R. As you can see here, the perpendicular distance from A is 0. There is no any distance R. So this is going to be 0 for our point A. Next we need to find our bending moment for point F. We are going to find our bending moment for point F, MF. and this is going to be 10 into 2. This is 2 meter. So as you can see from my question, so this is acting at a distance of 2 meter. So this is going to be 10 into 2. So next we have our direction, whether it's going to be clockwise movement or anti-clockwise movement. As you can see here, this is acting vertically downward, and it's going to produce our anti-clockwise movement. And while moving from left to right, clockwise movement is positive while our anti-clockwise movement is negative. So this is going to give me anti-clockwise movement, or our hogging bending is going to be minus 10 into 2, is minus 20 kN per meter. So let me, in order to explain our bending moment a little bit clearly, what we can do over here is, so as you can see here, while moving from left to right, we are going to take our, this is going to be my sagging bending moment, and this is going to be my hogging bending moment. Our sagging bending moment is taken as positive, while our hogging bending moment is taken as negative. So what is, so as you can see, in our sagging bending moment, our beam is moving upward. So we have our movement in this way. It's our left, this is our right, this is our left, this is our right. For our hogging, we have our downward. Our beam is moving downward. It's going to be my moment. It's going to be my moment. So while moving from left to right, for our sagging bending moment, we are going to take our clockwise movement as positive, while moving from left to right, where our anti-clockwise movement is going to take as negative. So this is how our sign convention works for our bending moment. Left to right, sagging means our beam is moving upward. So as you can see here, our beam, this is our beam, it's going to move upward direction. Our beam is going to move upward. So we are going to take this moment, clockwise moment, as positive, while moving from left to right, our anti-clockwise movement, which means our hogging, our beam is moving downward. So we're going to take our bending movement anti-clockwise. We're going to take, in this case, our anti-clockwise movement as negative. So hope you have understood how our sagging and hogging works for bending moment. So next, what we are going to do is, we have taken this as minus 20. Now we need to find our bending moment at MB. So as you can see here, from MB we have over here B. So as you can see here, 30 is acting downward, 30. So let me show it in this way. So as you can see, we have 30 kN over here, and we have my distance of 4 meter, while from my distance of 10 kN is 2 meters. So as you can see here, for my point B, both are going to produce anti-clockwise movement. So as you can see here, if I fix my pen at point B, and if I move 30 kN, both of them are moving downward, producing anti-clockwise movement. And while moving from left to right, anti-clockwise movement means hogging, which is going to give, which I am going to take as negative. So MB will be simply equal to minus 30 into distance 4 minus 10 into distance 2. So this is minus 30 into 4 minus 10 into 2, which is going to be equal to minus 140 kN per meter. So let me write this down over my figure. So as I explained before, this is going to be my very most important figure for my whole frame analysis, because now we are going to update my figure. So as you can see here, what I got from here is, from my joint B, I have my hogging bending. Hogging means negative bending moment of minus 140 kN, and on our hogging bending moment means anti-clockwise bending moment. So for my member AB, since this is going to be my anti-clockwise, so as you can see here, this is my member AB, this is my clockwise direction, this is going to be my clockwise, this is going to be my clockwise direction. So my bending moment is acting anti-clockwise, so this is going to be my anti-clockwise direction. So let me write down my force of minus 140 kN per meter. So now I have shown my bending moment of minus 140 kN, or hogging, or negative bending, or anti-clockwise movement at joint B. So now another important point of joint is joint transverse bending moment. Transverse bending moment, or simply our moment, our joint simply transfers our moment. So this minus 140 kN meter, this moment acting in anti-clockwise direction for our member AB is going to get transferred for our member BC as well, because of our joint. Since our joint transfers our bending moment, so we are going to have our anti-clockwise moment of 140 kN meter at for our point B as well. So let me write it down in this way, minus 140 kN per meter anti-clockwise bending moment. So why is this? Because I have already explained this before. Let me say it one more time. For our member AB, for at a joint B, we have our anti-clockwise or a hogging moment of 140 kN meter, and our joint transverse moment. So for our member BC, BC, we are also going to have our anti-clockwise or hogging bending moment of 140 kilonewton meter. So you have understood why I have written 140 kilonewton meter over here. Next, what I need to do is, now I have completed my member AB. Next, I'll consider equilibrium of member BC. After completing member AB, now we move towards member BC. So now this is our figure looks like. We have our additional 140 kilonewton meter acting anti-clockwise in our joint B. So now we consider equilibrium of member BC. Let me write it over here. Consider equilibrium of member BC. Consider equilibrium of member BC, and let me draw my figure of for member BC. So this is what my figure looks like for member BC, and I need to draw this figure. So for my member BC, I have a point E over here where we have a clockwise moment of 10 kilonewton per meter. And as I explained before, since joint transverse load in my joint B, I am going to have another anti-clockwise moment of 140 kilonewton meter, and we write down all the remaining forces. 40 kilonewton, since this was acting downward for since 30.57 was acting downward for member AB, this 13.57 will act upward for member BC in order to maintain equilibrium. So 13.57 kilonewton acting upward and 13.57 kilonewton acting downward at over joint C, and we have 10 already done, so 40 and 40. So these are all the forces for my member BC, and with all these forces I need to calculate my axial force, shear force, and bending moment. So firstly, we'll be following the same sign convention as I explained before. So firstly, I'm going to calculate my axial forces. Axial force for my member BC. Axial force NBC, let me write it as NBC. This will be equal to, as I already explained before, axial force are forces acting along your axis or along your member, and along our member we have 40 kilonewton, and previously as for our member AB, this 40 kilonewton are of compressiveness as the writing inward. So we are going to write this as minus 40 kilonewton, and in the bracket we can put compression. Next we are going to calculate our shear forces. Shear force. So right now we are moving from left to right, from member B to C, and moving from left to right, I'm going to take VVL. As you can see here, at left of B there are no any forces, so VVL is going to be equal to 0 kilonewton. So now I'm going to take for shear force right of B, BV right. As you can see here, as I already explained before, shear force are those forces which act perpendicular to your beam. So as you can see here, perpendicular to our BC, we have force of 13.57 kilonewton, and it is acting upward. And as I explained before for my sign convention, while moving from left to right, we are going to take upward forces as positive and downward forces as negative. So 13.57 kilonewton is going to be taken as positive. So 13.57 kilonewton. And now we are going to move at directly we are going to move till C, because between B and C there are no any forces acting perpendicular, so we don't need to take any other point. So now I am moving directly to left of C, and left of C I am going to have 13.57 kilonewton only. So you can end it over here only for our shear force, but in order to, we can take one more point at right of C, and it's going to be 13.57 minus 13.57, which is simply going to be equal to 0 kilonewton. So why this is taken down is taken as negative, because this is acting downward, and while we move from left to right according to our sign convention for beam, downward forces are taken as negative. So 13.57 minus 13.57 will simply equal to 0. Now at last we are going to calculate our bending moment. So in order to calculate our bending moment, we are going to take a shortened section. We are going to find our bending moment about B, MB. So we are going to take a shortened section, and while taking a shortened section, where we are going to take our shortened section? So that's a confusion which is among many students. So in order to take our section, we are going to take a shortened section XX, but where are we going to take our section? Are we going to take it over here, or are we going to take it over here, or over here? So in order to answer that question, we are going to take our section XX, where we can include or incorporate maximum number of forces. So as you can see here, if I take my section XX over here, this 10 kilonewton per meter is going to get avoided. So if I take my bending moment, take my section XX over here, all my forces are going to be included for our bending moment of B. So simply we are going to take our section at over here. So next what we are going to do is we are going to we're going to take our bending, we're going to calculate our bending moment, and while calculating our bending moment, while moving from left to right, we take clockwise movement as positive and anti-clockwise movement as negative. So our, so not mb, so mx will be equal to, so we are moving from left to right, we have our first force of minus 13.57. so this is at a distance of x. So right over here, so we have our first is 13.57, and with respect to our xx, 13.57 is acting upward, which means producing clockwise movement, and while moving from left to right, clockwise movement means sagging, which means positive. I have already explained why this before. So 13.57 into x minus 140, we have this 140 Newton meter, but we are going to take it as negative since it is acting, since it is producing anti-clockwise or hogging moment. So minus 140, and next we have 10 Newton, and we are going to take this as positive because clockwise, moving from left to right clockwise. So next we have this will be equal to, so now in order to find our bending moment about B, so as you can see here, while finding out our bending moment about B, we are going to have a different so it's going to be 135x minus 140. So while finding, this is going to be our bending moment, so bending moment over for our overall beam, but but in order to find our bending moment for our portion B, we are going to have to take our section over here, because we do not need to include our 10 kN per meter. So we need to see section over here only. We do not need to include 10 kN per meter. So 10 kN per meter is not going to be included. So we are going to exclude that, and we are going to put on this only. So let me put now x, when x equals to 0, bending moment about B will be equal to minus 140 kN per meter, and when x equals to 2, bending moment about E will be equal to 13.57 into 2 minus 140. This is going to be equal to minus 112.86. So till over here, till over E, we use this formula 13.57 into x minus 140. But as we move our section right of E, we need to include our 10 kN per meter as well. So we are going to use this formula. Hope you have understood why I have kept two different general formula. So I have kept two different general formula. One is till E and one is for after E. For till E, we do not need to include plus 10 kN per meter. But as we move right of E, we need to include this as well. So for our MB and ME, we use this formula. But now as we move right of E, we need to include this 10 kN per meter as well. So when x equals to 4, bending moment equals to 4 meters. This is in meter. Bending moment about C will be equal to 13.57 into 4 minus 140 plus 10 as well, and it's going to be equal to minus 75.72 kN per meter. Now our figure, this figure is going to get again updated, because we have at C we have minus 75.72 kN per meter. And as I already explained before, joint transfer our bending moment. So for our member CD as well, we are going to have our anti-clockwise moment. So we are going to have our anti-clockwise moment of 75.72. So for our member CD, this is going to be my clockwise moment, this is going to be my anti-clockwise moment. So let me put my 75.72 kN per meter. So going to be my anti-clockwise moment of 75.72 meter transferred over here. So next we have now we are going to find our equilibrium for our member CD. We have completed for our member BC. Now we need to go for our member CD. After calculating our bending moment at C, we found this as minus 75.72 Newton per meter. And what we're going to do next is we are going to put that minus 75.72 for our member CD. So as you can see here, for our member BC, we found that the bending moment at C is minus 75.72, which means it is going to produce our hogging bending moment acting in this direction. So for our member CD, as I explained already before, joint transfer moment. So from our BC, this 75.72 is going to get transferred for our member CD as well. So minus 75.72, which means our hogging bending moment, which means upward. So our beam is going to move. In this direction, in downward direction. In this direction, our beam is going to move. This is our hogging bending moment. So which means in this direction our moment is going to act. So minus 75.72 will be acting in this direction for our point, or for our joint C. Minus 75.72 acting in So we have our minus 70.572 acting in anti-clockwise direction. This is our clockwise direction for our member CD. So this is going to be our anti-clockwise direction, minus 75.72 kilonewton per meter. So we have added that bending moment. So now our forces have been completed for our overall frame. Next, what we are going to do is we have completed our equation of equilibrium for AB, BC. Now we are going to consider our member CD in equilibrium and calculate our shear force, axial force, and bending moment. So now, as explained before, we are going to consider our equilibrium for our member CD. So for our member CD, we are going to consider our equilibrium. So let me write over here, consider equilibrium for member CD. Consider equilibrium for member CD. So let me draw my figure first. So let me draw my figure. So this is my CD. I have a force of 50 kilonewton acting over here, 50 kilonewton, and I have my moment of 78.72 kilonewton per meter. So this is my figure, 75.72, 75. So I have my moment of 75.72 kilonewton per meter, and remaining what I have is what I did not include previously is, since I have a force of 40 kilonewton acting at left of C for member BC, so for my member CD, a force of 40 kilonewton must act at the right in order to maintain equilibrium, as for our AB and BC case. Similarly, there was a force of 13.57 kilonewton acting downward for my joint C for my member BC. So for my member CD at joint C, 13.57 kilonewton must act upward in order to maintain equilibrium. So 13.57 kilonewton must act upward, 13.57 kilonewton is acting downward, so upward, 40 kilonewton acting at left, so must act at right. They must act in opposite direction in order to maintain equilibrium. So I need to put on that as well. 13.57 kilonewton acting upward. So let me put it this way: 13.57 kilonewton acting upward, and my force of 40 kilonewton acting at right. So I have my theta over here, and I have my RDY as well, which we calculated at step first, and we found it as 16.43 kilonewton, 16.43 kilonewton. So right now what I need to find is, I need to find now my axial force, shear force, and bending moment. So as I explained before, axial force are those forces which act along my member CD. So as you can see here, right now I do not have any force acting along member CD, and next is my shear force, which is acting perpendicular to my member CD. So as you can see here, 16.43 is acting in this direction. So in order to find my axial force, what I simply need to do is, I need to resolve my 16.43 in this direction. I need to resolve my 16.43 along CD. So I need to find my cosine and sine component. So right now what I'm going to do is, I'm going to take my joint D. I can take joint C as well. I can take either joint C or joint D. So as you can see, there's just one force acting at joint D, but there are two forces, 40 and 13.57 kilonewton acting at joint C. So it's going to be a bit complicated. So right now I'm going to take my joint D in order to show the process faster, in order to solve it quickly. So right now what I'm going to do is, I'm going to take joint D, and I'm going to resolve my 16.43 kilonewton into its sine and cosine component, so that I can calculate my shear force and axial forces. So for joint D, so let me draw my figure for joint D. So this is what my joint D looks like, and this is my member CD. I need to find my forces along it. This is my member CD. So what I have is, I have theta over here. So this is going to be 90 minus theta. This is going to be theta. Then this is again 90 minus theta is going to be theta. 90 minus theta, theta. So theta occurs alternatively. So what I have over here is, I have my so I have my force of 16.43 kilonewton acting upward. 16.43 kilonewton acting upward. So what I'm going to do is, I'm going to resolve my 16.43 into cosine and sine component. So this is going to be 16.43 cos theta. Nearer is going to be always cos, and the farther is also going to be sine. So giving this direction, this is going to be 16.43 cos theta, which is this value is equal to 9.86 kilonewton, and this is going to be 16.43 sin theta, which is equal to 13.14 kilonewton. 13.14 kilonewton. So as I already explained before, shear force are those forces which act perpendicular to our member CD. So as you can see here, since our member CD is inclined, our shear force also must be inclined at certain direction. So this 16.43 is not going to produce shear force, because it is acting at vertically upward. So it must be inclined at an angle theta in order to produce our shear force as well. So for our shear force as well, we need to resolve our forces. So this 16.43 sin theta, this is going to be our cosine theta, which is 13.43, which is acting our along, which is 13.14, which is acting our member CD. This is going to produce axial force, while this force of 9.86, which is acting vertically upward at an angle of theta, this is going to contribute for our shear force, and we'll talk about shear force later on. So firstly, we're going to talk about our axial force only. So this figure is a little bit complete. This is a little bit messy. So let me draw my figure this way. So after resolving, I get my 13.14 kilonewton over here, and next I got 9.86 over here. So after resolving my 13.14, after resolving my 16.43 kilonewton, I got these two forces. So this is my member, this is my joint D, and somewhere in the middle I have 50 kilonewton. So as I already explained before, in order to maintain equilibrium for my joint C in this direction along axially, another force of 13.14 kilonewton must act in this way in order to maintain equilibrium. So I can put another force over here. So as you can see here, 50 kilonewton is acting downward, while 9.6 is acting upward. So my resultant is going to be downward force of 50 minus 9.86, which is equal to, and this is going to be equal to 40.14 kilonewton. So in order to maintain equilibrium for my joint C, a force of 40.14 kilonewton must act upward. 40.14 kilonewton must act upward. Hope you understood this concept. 9.6 is acting upward, is acting perpendicular to member CD, and 50 kilonewton is acting downward. So in order to maintain equilibrium, 50 minus 9.86, which means a force of 40.14 kilonewton is acting downward. Hence, to prove equilibrium, a force of 40.14 kilonewton must act vertically upward. So taking joint D, I can do this, and now I can move on to calculate my axial force and shear force. Next, what I can do is I can also take my joint C. So let me take my joint C. Joint C is going to get a little bit complicated because there are two forces being involved. So let me put on my joint C as well. You do not need to do for a joint C as well. After doing your joint D, you can do this, and you can move on to calculating your axial force, shear force, and bending moment. But to show how this can be done through joint C, I'm going to show this. So if I do my joint C, I'm going to get my same value of 13.14 and 13.14 and 14.14. But let me show you quickly how this is done. So in my joint C, I have my force of 13.57 kilonewton acting upward, and a force of 40.140 kilonewton acting in this direction. And as you can see here, I have my this angle as theta. So let me resolve my force again. So this is going to be theta. If this theta is going to be 90 minus, this is going to be 90, this is going to be 90 minus theta. If this is 90 minus theta, this is going to be theta. If this is theta, 90 minus theta, theta, theta. So as you can see, we can find an angle this way for my joint C as well. Theta 90 minus theta 90 minus theta 90 minus theta, since this occurs alternatively. So right now I have my force of 40 kilonewton acting in this direction, and I have my 13.57 acting in this direction. So if this is 40, this is going to be its cosine component, 40 cos theta. The nearer component is always going to be cosine component, while the farther component, this component is going to be sin theta, 40 sin theta. Similarly, I need to resolve my 13.57 as well. Nearer 13.57 is acting in this direction, vertically upward. So this so I have my theta 90 minus theta is going to again be theta. So 13.57, so plus 13.57 cos theta, while this is going to be my 13.57 sin theta sin component. So as you can see, or what you can clearly see, 13.57 nearer component is 13.57 cos theta. It is going to get added to 40 sin theta, while 13.5 sin theta, another component is this, which is 13.5 sin theta. So I am going to have my resultant figure. Let me draw one more resultant figure, which will look quite like this. This is my member CD. So I got 40 sin theta plus 13.5 cos theta, and this is going to be equal to 40 sin theta is 32, while 13.5 cos theta is 8.14. So if we add both of these, I am going to get 14.14 kilonewton. As I explained before, 14.14 from my joint C, I got the same value. While for my there is another force of 40 cos theta is acting downward, while 13.5 cos theta is acting in opposite. Both are acting in different direction. While the value of 40 cos theta is 24 kilonewton, while the value of 13.5 cos theta is 10.86. So my resultant force is going to act in the direction of 24 kilonewton, which is 24 minus 10.86, and that is going to be equal to 13.14 kilonewton. So you can use the joint C as well. We're going to get same value, but using joint C is going to be a little bit more complicated because of two forces involved. You can use because of the more forces involved. So now what we're going to do is, now after finally doing, you can, as I explained before, choose joint D because it has less amount of force, and we are going to draw this figure. So now we are going to calculate our axial force. Finally, we are going to calculate our axial force for our joint D. So for our member CD, we are going to calculate our axial forces. So our axial force NCD is going to be equal to minus 13.14. I have already explained why, because this is of same nature, compressive. Now for our shear force. Now for our shear force, we are going to find our shear force at C. We are moving in left to right, and while moving from left to right, upward force are negative, while downward force are negative. While moving from left to right, so at VC, so let me write BCL is 0 kN, but let me move to PCR. So what is my PCR is, I am moving from right. So as you can see here, as I already explained before, shear force are perpendicular forces. So the force perpendicular is 40 kN, not 13.5 kN. 13.5 kN is acting vertically upward. For our, since our member CD is inclined, so our vertical force also must be inclined. So they also must be inclined. So we have our inclined force of 40.14, and this is acting vertically upward. So while moving from left to right, vertically upward force are taking positive, so 14.14. Next we move move directly to our left of D, VDL. So we have VDL is 40.14 minus 50, since 50 is acting downward. While moving from left to right, downward force are taking negative, so 50.14 minus 50 means minus 9.86 kN. And finally at the right of D, we have minus 9.86 plus 9.86, which is 0 kN. Hope you understood this, because we have 9.6 acting vertically upward. So our shear force is complete. So finally we are going to get our bending moment. So in order to calculate our bending moment, we can take our shortened section, or we can do this directly as well. So let me just do it directly. So we are going to take our bending moment at about C, at our point C, bending moment at our point C. So here is our 75.72 kN. So as I explained before, this force 75.72. so for our bending moment, we have the 75.72 from our joint C, which is transferred over for our member CD. So for our C, we are going to have this moment only, negative 75.72. As we move little bit to our, now I'm going to get my bending moment about D. Bending moment about D is 75.72. So next we have this 40.14, and 40.15 is producing clockwise movement with respect to point D. 40.15 is producing clockwise movement, plus 40.14 into my distance is 5 meters. So I calculated this in my first. So I found where is it? Here is my length CD is 5 meter. So this CD is going to be 5 meters. So we are going to have plus 40.14 into distance CD, my perpendicular distance CD, which is 5 into 5. And my 50 is going to produce my anti-clockwise movement, so minus 50 into 2.5. Why 2.5? Because this 50 kN is acting at middle, it's acting at a midpoint, as I already explained in the first, as I already explained earlier. So 50 into minus 2.5. Why minus? Because it's producing anti-clockwise movement. Minus 50 into 2.5, and we are going to get this as 0. So in this way, we have calculated our equilibrium for member A, B, B, C, and CD for every member. So at the last part, what we are going to do is, we are going to draw our axial force diagram, shear force diagram, and our bending moment diagram. So let me draw my axial force diagram over here. So now in order to draw our axial force diagram, we are going to have a look at our individual members. So let me just, what we can do is, we can draw your figure firstly, AB, BC, and CD. So it's going to be AB, BC. So A, B, C. This is going to be my axial force diagram. First of all, it's going to be my axial force diagram. So as you can see over here, for my member AB, I found my axial force of minus 13.57. So for my negative, I'm going to show it downward, minus 13.57. You can draw it upward as well, negative 13.57. For my member BC, I found a negative. Again a negative axial force of 40 kN. So negative again, minus 40 kN. And for a member CD as well, we found our axial force to be negative, and it was 13.14. Negative 13.14 kN. So our axial force diagram is completed. So now we're going to draw shear force diagram. Shear force diagram. So again we're going to draw our member AB, member BC, and for our member CD. A, B, C, D. So now we'll be drawing our shear force diagram for our member AB, BC, and CD. So what I found my shear force was, shear force at A was 0, then it was minus 30, and it was minus 40 at F point. So at F point it was minus 40, so it was all negative. So I'm going to show my negative downward. So at first it was minus 30, so it remained constant, and again at F point, this is going to be my F point. At F point it got down to minus 40 and finally up to 0. So negative, so it's negative, so this is minus 30, this is minus 40 at point F, and finally 0. Now for my member BC, so for my member BC, we found our axial forces, we found our shear forces to be equal to 13.57, but it was positive. So positive means upward, so we are showing negative downward, so positive is going to be upward, 13.57 upward, and it was constant until it became finally 0 at point C. So in this way we are going to show it positive, which is 13.57 kilonewton. Just kilonewton. As you can see over here, our shear force was 13.57 at right of B, and it remained constant until it was finally 0 at C. Now for our member CD. So for our member CD, we found our shear force to be 40.14 minus 9.86 and finally 0. 40.14 minus 9.6 and finally 0.14 and minus 9.86. So for our C, we have 40.14 kilonewton, and it decreased, and shear force got 0 somewhere until for our point D it was minus 9.86 kilonewton until it became 0. Positive, negative. This is my shear force diagram for my member CD as well. Now finally, now what I need to do is I need to draw my bending moment diagram. AB, BC, CD. This is my bending moment diagram. You need to draw this at the end when you get all your data. So for my member AB, I found my bending moment of 0, minus 20, minus 140. So I'm going to draw my bending moment of negative upward. You can draw downward as well, but as you can see here, if this is now for our sign convention for our beam, you can find was, so for my member AB, I found my bending moment of 0, minus 20, and minus 140. We're going to take minus upward. We're going to take minus upward for our bending moment. Which is why, because let's say we have a beam over here, and as I already explained my concept of sagging and hogging. So if the bend moves downward, it is taken, this is sagging, but if the beam moves upward, so if we have this sort of bending moment, this is taken as, this is our hogging, this is our hogging, and this is taken as negative. So if this is my beam, and if it is negative, which means it needs to move upward, it needs to move in this way. This is my beam, it needs to move this way, which is hogging, as you can see here, this way. This is sagging, which is positive, but right now we have hogging, which is negative, which means upward. So this is my upward direction. So right now if I'm seeing this, so if I am observant over here, and if I'm seeing this beam, the hogging means it is moving upward in this direction. So I'm going to show my direction of bending moment this way. You can show your bending moment downward as well, but to understand, but in actual we need to show it in upward. So right now I have my bending moment of 0, minus 120, minus 140. So at F I have, so let me take my point F, which is at point F I found this to be equal to minus 20, then minus 140. So minus 140, and this is going to be directly joined this way. So for my point F, this is negative, this is minus 140 kilonewton meter, and this is going to be minus 20. And similarly for my next we are going to see for my member B. So for my member BC, I found my bending moment of minus 140, minus 112, and minus 75.72. This all are hogging. Negative means hogging. So as I explained before, hogging means upward. So I'm going to show that, so all those bending moment. Firstly for my minus 140, and it's going to get a decreased, and finally up to 0 over here. So I have point E. So in point E, I found my bending moment to minus 112.86, while for my B is minus 140, while for my minus 140, It's not zero, it's not going to end this way. We're going to have this way. It's going to be our, it's what going to be our, we're not going to end in this way because we have a negative of because over here we have minus 75.72, not 0. This is what, this and this, not over here, both negative, not this way. So this is what my bending moment looks like for my member BC. Now for my member CD, we need to draw our bending moment. We don't have this portion, this was a mistake. So for finally for my member CD, I have member CD, we have found our bending moment to be minus 75.72 and 0. Minus 75.72 at C. So let me draw, let me put on this way. Minus 75.72 over here, and this is going to be 0. But this is not going to be linear, this is going to be parabolic. 0. It's also negative. Negative is upward. So why parabolic? Because we have UDL, uniformly distributed load, and for our UDL, the nature of our bending moment is going to be parabolic, not linear, but we're going to have parabolic for our UDL and cubic for our UVL. So right now in this way we can solve. We have done our frame analysis. Hope you have understood how all this was done, and if you have any queries, you can comment down below. And if you like our video, do subscribe our channel and like our video. Thank you.